So this actually generalizes to nonlinear hyperplanes using polynomial generalizations. In the left-hand side, I'm giving an example of points x that are in R2. So here x is a first dimension and a second dimension. Then I have a linear classifier, and I define all points on one side to be class 1, all points on the other side to be class 2. So for example, perhaps class 1 corresponds to the positive sign and class 2 corresponds to the negative sign. Now, if I perform an expansion of my features, so for example, if I take my input vector that's two-dimensional and I transform it so that the first two dimensions are the original vector, and then the second two dimensions, so the third and the fourth dimension, are the squares of those inputs. And now I do linear classifier, binary linear classification in R4. What I'm doing is finding a hyperplane in R4 to separate these four-dimensional vectors. But if I look at the decision boundary projected back to R2, I would get something that looks like this. So the feature expansion, or this four-dimensional expansion of any two-dimensional point on the right-hand side would be classified as class 1. And that same four-dimensional vector constructed from any point on the left-hand side here would be classified as class 2, because every point to the right of this decision boundary maps to R4 in a way such that it's linearly separable in R4 from any point here mapped to R4, according to this expansion. And we actually saw an example of this with the Bayes classifier, where each class conditional density was a multivariate Gaussian and had its own mean and also its own class-specific covariance. So let's go back and look at that, similar to how we did with the linear case. So if we look at the log odds for a specific case where the class conditional density is a multivariate Gaussian with a mean and covariance specific to that class, and we now assume that we have two classes, class 0 and class 1, and we input the class-specific Gaussian density here and here for the two classes, as well as the priors, the class priors, and we actually calculate this mathematically. What we'll find is that we get something that is a constant that doesn't involve x, so that corresponds to W naught. We get a linear term. We get a part that is a vector dot product with an input x. And we get also this quadratic term. We get a term that is x transpose times some matrix times x. So this is quadratic discriminant analysis. So we saw this last lecture as well. In this case, we would declare class 1 if the sign of a quadratic function is positive, where a is defined to be equal to this, and b is defined to be equal to this, and this is c. So we have something that looks like this. If the sign of that function is positive, we declare class 1. If it's negative, we declare class 0 or minus 1. What we can show is that actually this is linear in all of the unknown weights, a, b, and c. Similar to our discussion in regression, this is also a linear classifier because the weights that we need to learn, a, b, and c, are all linear. They all interact linearly with our data. A quick way to see that would be to imagine this type of a transform of x in R2. Let a two-dimensional input x be mapped to 5 dimensions now, where the first 2 dimensions are the original data. The third dimension is 2 times the product between those 2 dimensions. And then the fourth and fifth dimension is the square of the dimensions of our input x. We can see that actually what we're doing with this quadratic function is a linear classifier in the higher dimensional problem. And so that's where we see that learning a linear classifier in that 5-dimensional space maps to a nonlinear function in the original 2-dimensional space. So it's again an instance where a linear problem is hiding underneath something that looks like a very nonlinear problem.